Hi class, today we're going to be in a new section. It's going to be rational functions, and today we're going to be taking a look at the domain, asymptotes, and point discontinuities. So today you guys are going to be able to find the domain of a rational function, find the vertical asymptotes of irrational functions, and find the point discontinuities of a rational function. Now, the definition of a rational function is basically a function which the ratio of polynomial functions. Okay, so here's polynomial function 1, polynomial function 2, and you're dividing them. Now, there is an issue here. Remember from previous sections that when you potentially divide by x, there's a chance for us to get 0 in the denominator. Well, that is a restriction to our domain. And so we have to keep that restriction in mind as we go forward, because that's going to be a way that we can describe our function. It's going to be through those domain restrictions. So we're going to practice that first. It says find the domain of the following rational functions. Write them in the form p of x over q of x for the polynomial functions p and q, and simplify. Okay, so finding the domain, we can't divide by 0. So I basically take whatever's in the denominator and I say it can't be 0. So I'm going to say x plus 1 can't be 0. Solve for x. We say x cannot equal negative 1. Now that means that on the number line, remember, we have negative 1. It's an open circle, but we never said the other values can't be true. And so my domain is going to be from negative infinity to negative 1 union from negative 1 to positive infinity. Now it's already in the form of p of x over q of x, so there's not much more I need to do with that. Our next problem here, once again, taking a look at what we're dividing by. Well, this is dividing by 1, that's okay. Over here, once again, x cannot equal negative 1. So I'm still going to have that same domain from negative infinity to negative 1, union from negative 1 to positive infinity. So I'm still going to have that same domain, nothing changed there, but now I need to manipulate my equation and put it into this p of x over q of x. All we're going to be doing here is we're just going to combine these together. We're going to find the common denominator and actually perform the adding or subtracting operation. So the common denominator is x plus 1, and so that term needs x plus 1 over x plus 1. Now if I distribute, I'm going to get 2x plus 2 over x plus 1 minus 3 over x plus 1. So 2 minus 3. And that right there is going to be my answer. It's in the form of p of x over q of x. Next one here. Okay, once again, if we take a look at this, I have to say this cannot equal 0. And same here, this cannot equal 0. Well, if I solve for this one, I get x squared cannot equal positive 1. So if I square root both sides, x cannot equal negative 1 and positive 1. But if I do this side and square root that, x cannot equal plus or minus I. Well, that's an imaginary value, so there's no intersection between x squared plus 1 and 0. And so this, basically, the way that we interpret that is, okay, I'm not going to get any values that restrict my domain there, but I do have values here. So if we envision that on a number line, remember negative 1, open circle, positive 1, open circle. The rest of this gets shaded in. So my domain is going to be from negative infinity to negative 1 union, from negative 1 to 1 union, from 1 to positive infinity. Now I need to write it in the form of p of x over q of x. So this one's going to be a little bit more complicated, but remember we still have to do the same thing. We want to find the common denominator. So if I factor this, this factors into x plus 1 times x minus 1. Okay, so the x squared plus 1, that doesn't factor. So this right here, this needs x squared plus 1. This here needs x plus 1, x minus 1, x plus 1, x minus 1. So now I get to spend that lovely time multiplying everything through. So distributing this, x squared and 2x squared, that's going to give me 2x to the fourth minus x squared plus 2x squared minus 1, and then minus, now this is just going to be x squared minus 1. Let's treat it like that because it's going to make things a little bit easier for us. And this is going to be x squared minus 1. So if I multiply those through, 3x times x squared is going to give me 3x cubed minus 3x minus 2x squared, and then plus 2 all over. Now x squared times x squared is x to the fourth, and then so I'm basically doing x squared times x squared times negative 1 plus x squared and minus 1. So those cancel out immediately. That's nice. But let's distribute this. So if I change that to a plus, then that's a minus, that's a plus, that's a plus, and that's a minus. So now let's try combining like terms. I don't have any other x to the fourth, so I have 2x to the fourth on top. Then negative x squared, so that's positive x squared. And then I have another one too, so it's going to be positive 3x squared. And then I do have a negative cubed, so let's do that. So plus 3x squared. I do have a minus 3x cubed. And then I have a plus 3x, and then a minus 3. And this is all going to be over x to the fourth minus 1. So I have my p of x over q of x. Now this one here, this is going to be forms of division. But notice, okay, just remember, we have to be a little tricky with our division. We have to change it into the form of multiplication before we look at it in terms of our denominator. Now, this is what I mean. We have 2x squared minus 1 over x squared minus 1 divided by 3x minus 2 over x squared plus 1. Now the issue here is that there's technically a bunch of denominators going on. I have a denominator here, so that's a denominator that I need to pay attention to. I have a denominator here, that's another thing that I have to pay attention to, so that should be a 2. And I have a denominator here that I need to pay attention to. All three of those denominators give me a potential of dividing by 0. So I have to pay attention to that. Before I even try and reduce this, I need to pay attention to that in terms of the domain. So I have x squared minus 1 cannot equal 0. I have 3x minus 2 cannot equal 0. And then I have x squared plus 1 cannot equal 0. Well, we already determined that that's going to be negative 1 and positive 1. If I solve for x here, this is going to give me 2/3. And then for this bottom one here, remember we said that there's not going to be any zeros that it gives us. So plotting that on the number line, negative 1, 2/3, 1. We said that these are all open circle, and my graph is everything in between. So my domain is going to be from negative infinity to negative 1 union, from negative 1 to 2/3 union, from 2/3 to 1 union, from 1 to positive infinity. Now, writing it in the form of p of x and q of x, so we're going to have to go through and we're going to have to simplify this. So remember, is there anything that could cancel out? Well, so far, no, nothing cancels out. So that means that as a shortcut, remember this gets flipped. So those end up getting multiplied together, and those end up getting multiplied together, right? Because we have to flip it and change it into multiplication. So that means I get 2x squared minus 1 over x squared minus 1 times x squared plus 1 over 3x minus 2. So now multiplying everything through, you get 2x to the fourth plus 2x squared minus x squared minus 1 over 3x cubed minus 2x squared minus 3x plus 2. And so now simplifying that, 2x to the fourth plus x squared minus 1 over, and you get your 3x cubed minus 2x squared minus 3x plus 2. And that right there is going to be how we turn it into p of x over q of x. So now let's take this a step further, because we now understand what the domain is. Now we have to kind of pivot and see, well, what does it look like? And so what if I take this function 2x minus 1 over x plus 1 and I graph it? And so if I enter it in your graphing calculator, you're going to get something like this. So there's actually two behaviors of this graph that we're going to actually take this to the next level and kind of talk about. The first, if you notice, there's kind of like this break here, right? This graph is approaching this number here, this graph is approaching this number here, and there's like this break here at x equals -1, okay? Now we're going to discuss the implications of this break in terms of end behavior later on, but we call this break a vertical asymptote. And so this break here, that's going to be called a vertical asymptote. Now the second is it appears that our graph is actually leveling off at this value and at this value here. Now, whenever it seems like our graphs are kind of leveling off towards a value like that, it's a type of asymptote. And so in this case, we're going to call it a horizontal asymptote. And we're going to find out in the following lesson how we find what our horizontal asymptote is. And then even further past that, we're going to discuss the leveling off in terms of end behavior. Now, how do we find this vertical asymptote, right? That was one of the first things that we mentioned. Now, luckily for us, we just practiced being able to find the domain of a rational function. Well, the vertical asymptote is part of that domain restriction. So a vertical asymptote is one of the domain restrictions of a rational function. It's the value for x that makes the function undefined except in the 0, 0 over 0 indeterminate case. So that 0 over 0 indeterminate case, that is something else. We're going to talk about that shortly. But anytime that it's a domain restriction that's not 0 over 0, that's a vertical asymptote. So in this case, what is my vertical asymptote? Well, the only possible way for me to get a 0 or an undefined value, right, is going to be to divide by that 0. So if I set my denominator equal to 0, I'm going to get x equals -2 and x equals 2, right? If I say that can't equal 0, that can't equal 0. So I'm going to get -2 and +2. But there's the issue here. That x equals -2, when I plug that back in, right, -2 plus 2 is 0 over -2 plus 2 is 0. I get 0 over 0. That's the indeterminate case. Therefore, it's not going to be a vertical asymptote. So this right here, that's not going to be a vertical asymptote. But that x equals 2, that gives me 4 over 0. And so therefore, that's going to be a vertical asymptote. And so I can say that I have a vertical asymptote at x equals 2. Now, a shortcut to note is that we should try and simplify our expression first. Every single time this 0 over 0 case, something's going to cancel out when it comes to a rational function like this. So if we simplify first, it will eliminate that 0 over 0 possibility. And so we would just end up having 1 over x minus 2, set the denominator equal to 0, and we're going to get that x equals 2, which is going to be my vertical asymptote. So in these cases, let's find the vertical asymptote of these. So this first one, remember, we have to try and reduce it. So this is going to turn into x plus 3, x plus 4, and this would be x plus 4, x minus 4. Well, that will cancel out, so those are not vertical asymptotes. I have this x minus 4 left in the denominator, so x cannot equal 4, so my vertical asymptote is going to be the equation x equals 4, because that's going to be in my denominator. For this one here, even though my graph will change when I combine these two together, we still only need to technically look at what's in the denominator. But what if something cancels out? I don't know if something's going to cancel out. In this case, we do know because we've already seen it, but sometimes it might be a good idea to combine our functions together, because if we don't, we might get that type of reduction where I'm saying like it could be like a point discontinuity of some sort. And so we need to combine these together. And so remember we said that this needed the x plus 1 over x plus 1. And so that gave me 2x plus 2 minus 3 all over x plus 1. So that became 2x minus 1 over x plus 1. Well, nothing's going to cancel out. And so there's my vertical asymptote. X cannot equal negative 1. That's going to be my vertical asymptote there. So now let's spend some time going over this 0 over 0 and taking a look at actually like what does it kind of mean. Now, whenever you get that indeterminate case, it means a point of discontinuity. And another common reference is we call it a hole. Now, if you notice, right, in this equation here, if I plug in both a negative 2 and positive 2, we get this undefined value, right? One of them was that 0 over 0 case. The other one was the 4 over 0. Now, because it was the 4 over 0, notice there's my vertical asymptote. And so that's why I have that imaginary dotted line there to represent this is the asymptote in which my graphs are going to kind of like hug and get close to. But what about that 0 over 0 case? Well, what ends up happening here is as we start plugging in numbers, everything on this side of negative 2 works, everything on this side of negative 2 works, as close as you get to that negative 2. But the moment that you get that negative 2, it's actually like this hole, and it's like this instantaneous hole that appears on that graph. And so that's why we call it a point of discontinuity, because it's an instantaneous point that makes our function discontinuous. And so that is actually how we draw it, right? Wherever my graph was, I drew a hole. That then visually represents that I have a point of discontinuity right there. And so just be aware of that. When you do get that 0 over 0, it's not a vertical asymptote. It's going to be that hole that I drew there. So for example number 4, it says state the vertical asymptotes and the points of discontinuity. So for this first one, I can factor. That'll turn into x and 2. Now remember, this is a difference of cubes, so it goes first times first is first, last times last is last, first times last is in the middle, isn't this a blast? The first sign's from the problem, the second's its reverse, the last sign's always positive no matter what the first, and on the bottom is x minus 2 and x plus 2. And so now these x minus 2's cancel out, and so that means I have a hole at whatever the 0 is. So technically I should take the x minus 2, set it equal to 0, and so I get x equals 2. So I have a hole at x equals 2. Wherever that is going to be on my graph, that's where I have my hole. Now to find my vertical asymptote, remember we just take whatever's left over, set the denominator equal to 0. Now if you're probably thinking, oh, does that factor further? It doesn't. But if I take that x plus 2 and set it equal to 0 and solve, you get minus 2 to both sides, so I get x equals negative 2. And so that's going to be my vertical asymptote. So there's a distinction. I have my hole or point discontinuity and my vertical asymptote. Now my g of x, so if I factor, I get x squared plus x plus 1 over x times x squared plus 1. Well, these cancel out, and so I do have a hole, and that's going to be at 0, but there's nothing else that cancels out here, and so I actually don't have any vertical asymptotes. And so that's going to be my answer. Now this does conclude our lesson. If you guys do have any other questions, please leave them in the comments.